Everyone, or, well, almost everyone, loves the sight of a model train rolling by. In recent years, model trains have taken on more and more of the presence of their full-size counterparts. How is this achieved under the hood? Or, in this case, under the shell? Let's pull back the magician's curtain and reveal what makes a model train work. To start off with, some things on model trains are exactly the same as they are on the full size. The wheels on model trains function exactly the same as the prototype. The wheels ride on top of the rails, and are kept on the rails by the wider lip of metal that sits just inside the rail on each side. These are called flanges. Likewise, model locomotives actually do the pulling. The entire purpose of a locomotive is to create rotational force applied to its wheels so that it can pull a train of wagons or cars behind it. The basics? Pretty much the same. But to attempt to machine 1,000 microscopic parts to make a fully functional 16-cylinder live diesel engine that is a mere 2 inches long would 1. Be a machinist's nightmare, 2. Instantly self-destruct the moment you tried to fire it up. While parts scale down, physics and thermodynamics do not. As such, model trains have to go their own way when it comes to propulsion, and over the years a very robust system has been more or less settled on. I will use this mechanism made by the Atlas Company to explain, but the basic principles found here are nearly universal across the vast majority of model trains. In the middle of the chassis is an electric motor. These motors function by energizing electromagnets so that they pull and push the rotor towards the magnetic poles. The electromagnetic poles then reverse, often as the motor brushes make contact with a different part of the commutator, and the motion continues until the commutator makes new contact and the poles reverse again. This happens hundreds of times a second when the motor is running at speed. At the ends of the motor on the driveshaft are machined flywheels. These serve to give the driveshaft momentum and smooth out any jerking in the motion created when the motor changes poles. The driveshaft extends from the flywheel through universal joints, which allow flexibility in the shaft while still transferring rotational motion. From here, the shaft connects to a worm gear, which is a cylinder with one long spiraling gear tooth. When rotated, the worm gear tooth meshes with and spins through a regular gear's teeth. This pushes the gear forwards or backwards, which transfers the motion down the gear tower and into the trucks, or wheel sets of the locomotive. This turns the wheels and makes the engine go. So what makes the motor go? Well, there are many different ways of regulating power to a model train's motor. For power and control systems based on direct current electricity, also known as DC, how fast the motor goes depends on the voltage applied to it, and its direction is determined by the direction of the electrical current. The simplest system for controlling a train is simple DC power control. Household alternating current, or AC electricity, is fed into a transformer and rectifier, which converts it to DC power. From there, it is metered out to the track according to the control knob on the transformer. This is why train set controllers are called transformers. The locomotive's motor draws power directly from the rails. However much power is in the track is how fast the engine will go. If you have more than one engine on that track, they will all go together, but whether their mechanisms move at the same speed is another matter. Over the years, model railroaders have sought out a more advanced method of train control. The gold standard is Digital Command Control, or DCC. On a DCC-equipped locomotive, a computer chip called a decoder reads constant power and signals from the track, then feeds power from the track into the motor as commanded. One could think of DCC as working on a principle similar to radio signals, but transmitted through the track instead of the air. Using square wave signals with varying distances between the highs and lows that translate to a binary code, digitized signals are broadcast through all the rails on the layout. These signals are picked up by decoders, which read them and act accordingly. Here is a computer readout of the activity within a Digitrax DCC system. Every decoder is assigned a numerical address. If two decoders have the same address, they will both follow commands sent to that address, which is great for a set of engines that will always run together, not so great when two members of a model railroad club have engines with the same number. Running a train on DCC feels more like being an engineer. On your throttle, you select your address, which tells the system which decoder to address your commands to. From there, you set your direction, turn on functions, and set your speed. Every one of those commands is received by the command station, sent out on the system in milliseconds, and the decoder acts according to the commands. Decoder functions can be anything from lights to sound effects and in some cases even servo motors. Decoders also exist for things like signals and switch machines. The DCC system can control it all, but for the sake of simplicity I will stick to locomotives here. Let's walk through the process of what happens to make a model go on DCC. The operator selects his address, sets his direction, and turns on functions, which are all registered and transmitted by the system. The operator throttles up, sending speed step signals through the track. The decoder picks up on the speed step command addressed to it, and energizes the motor with voltage appropriate to the speed step. The motor rotates, turning the drive shaft which spins the gears, turns the wheels, and away the engine goes. It happens this fast. In some cases, like the German company Märklin or American 3-rail O-scale, the trains are powered by alternating current, or AC, electricity. The digital versions of these systems work much the same as DCC systems. Analog AC systems have to get creative with changing direction, as AC power is constantly reversing direction and cannot by itself be used to reverse electromagnetic polarity. Analog AC-powered trains use a device to reverse the phase of the motor or sometimes energize a separate winding in the motor to change direction. Märklin used a device that flipped the direction with a voltage spike, while Lionel used an electromagnet and arm to rotate a mechanical drum to apply power to one winding or another in their motors. There are other systems out there beyond what I've talked about, such as radio control or live steam. But for the vast majority of model trains, this is how they work. So, the next time you see a model train rolling down the tiny rails, you'll have a decent understanding of what is happening under that shell.